Hi, this is Mr. Swanson, and today we're going to dive into our first topic called KMT. I highly recommend downloading the note catcher, which are guided notes for you to fill out as you go along. And you can see down here at the bottom the goals of by the time we are done with this video, you should be able to better understand KMT, temperature, pressure, and kinetic energy. Now let's take a look at a simulation of some molecules moving, and I want you to use your words to describe how these molecules are moving, and it might be helpful to just focus on one. And there's a trace on one of them just to show you what's going on. Alright, so as we're going on to explain the rest of KMT, keep in mind what these molecules looked like when they were moving around. The big word of the day is KMT, or kinetic molecular theory, and so I guess it's 3 words. But if we break that down, kinetic is talking about moving molecules or particles. We're describing anything that in chemistry is a molecule or particle right now. And then theory is this explanation of real-world phenomena. So that's where KMT, or kinetic molecular theory, comes down into. And to talk about KMT, we have to make some assumptions, because if we don't make them assumptions, the math is weird and the rest of the theory is a little bit too confusing. So if we simplify it a little bit, everything we're talking about is a tiny particle, and you can think of that as just like a dot on the screen. Okay, so everything is just like a dot. And it's in random motion. And so you saw that in the last video that these molecules would be back and forth hitting off of each other like pool balls. Next, we want to say that the average kinetic energy of the molecules, so think back to last year, is directly related to the temperature. So that's saying as the temperature is low, they are moving slowly. And as the temperature is high, they are moving faster. And finally, it is saying the fourth thing says the molecules are not attracted to each other. And this is not completely true, but it can simplify the model to make it easier. So this molecule there's no push or pull between these two molecules. It really depends on the molecule, but for now we're going to say there's no force of attraction between them. So why do we make assumptions? Let me dive deeper. Imagine somebody is going to give you this huge stack of money. And are you going to trust them, or are you going to count it all? Well, some of us might say we're going to count it all, but in reality, that would be a lot. So we can simplify it by just maybe taking one stack and counting it. And we can assume that if one of the stacks is right, the other one is right. Now, we might be off a little bit, but we're assuming it to make our life easier. That's what KMT is doing. It's simplifying the real world a little bit to make it easier to talk about science. So take a look at these pictures now. One represents a solid, one represents a liquid, and one represents a gas. And think back to what you know about how the molecules are arranged in a solid, liquid, and gas. Which one would you assign to which picture? If you said a solid for this one, and a liquid for this one, and a gas for this one, you would be right. And what you learned, hopefully last class, is that solids are nicely organized and very compact, not moving a lot. These are moving a little bit, sliding past each other, a little bit less dense. And finally, these are moving freely and bouncing off the wall and each other. So I want you to take a chance and draw on your note catcher what a solid, liquid, and gas would look like when you're doing it. And you're going to have to do this on the test, so it's helpful to do it right now. And the easiest way is to say, let's take a look at 10 molecules. For a solid, do you put the molecules up here? No, the molecules would be down there. Can you show your movement with a liquid? So if you have your liquid, you can show a little bit of movement. And gas molecules, you want to spread these out as far as you can, and you can show that they're making connections with the wall. So like a liquid, you wouldn't show that, because if you think about a liquid in a glass of water, it's not pushing up on the top of the water. So practice your drawings right now. A couple key facts that we're going to talk about is temperature and what temperature really is. Temperature is a measure of the average kinetic energy, and from last year, you know that is essentially talking about its velocity. So how fast it's going. So we would say they're directly related. So that means as the temperature goes up, so as the increase in temperature, that is equal to the increase in your kinetic energy. So they're related. When one goes up, the other one goes up, and when one goes down, the other one goes down. We'll talk about how temperature can be measured in degrees Celsius, degrees Fahrenheit, or Kelvin, but that will be the topic of a later class. So now, based on what you just heard, let's take a look at one example. We have 3 samples of water. Water at 10 degrees Celsius, 50 degrees Celsius, and 90 degrees Celsius. Which one is going to have the most kinetic energy? Which one is going to have the average molecules moving the fastest? Well, if you think back to what we said, when you increase the temperature, that also means you have an increase in kinetic energy. So which is going to have the highest kinetic energy? Water is, because it's at a higher temperature. Here's a slightly different scenario. We have 3 different substances: chalk, which is calcium carbonate, water, and methane gas. And what if they're at the same temperature? Let's say they're at 70 degrees Fahrenheit. Which one is going to have the highest kinetic energy? Well, might think of gas because it's methane because it's a gas, but the clue is they're at the same temperature. So increase of temperature is going to be an increase in kinetic energy. But if there's not an increase, if there's not a difference in the temperature, then they're going to have the same kinetic energy. So if you think about like touching 2 different substances in the same room, like maybe your metal chair and your wooden desk, even though they feel different, they're at the same temperature, so they have the same average kinetic energy. The last slide was a little bit of an oversimplification. How fast the particles are actually moving is going to depend on 2 things. If you remember from last year physical science, you know that kinetic energy equals 1/2 mv squared. So the kinetic energy depends on mass and velocity. So what this is going to end up meaning is that particles that are smaller are going to be faster. And that makes sense. Like a small car is going to be faster than a big truck because it has less mass to move around. So at a given temperature, so at a given kinetic energy, the velocity is going to be determined by the mass and that temperature. One of the most important words for this unit is pressure. And so we have to understand what pressure is. And so without going into a huge definition about it and talking about forces, what we can say is pressure is the force exerted from the molecule on the wall of a container. So anytime a molecule comes in contact with the wall, it exerts some kind of force. When a molecule comes in contact with another molecule, that's not going to affect the wall. So pressure is when a molecule comes in contact with a wall. And that's why a solid or a liquid, maybe in a balloon, is not going to put the pressure on the wall like a gas is, because those gas molecules are moving around a lot. So like we said, it's the number of collisions with the wall. That's a simplification, but that's easier. More collisions, higher pressure. So that's another direct relationship. Increase in collisions equals increase in pressure. So the different ways you can increase the number of collisions are if you add more particles, they're going to hit the walls more. If you shrink the space, the molecules are going to also hit the wall more because they have less distance to travel. And then if you increase the temperature, these molecules suddenly go faster. And so they're going to have more pressure as well. So these are the three easy ways to increase the number of collisions and thus the pressure. So let's try to combine this. Why does the pressure increase when the temperature increases? And there's a couple words we want to use in our explanation. When the temperature increases, the movement of the particles will increase. So we want to write increase. And therefore, the number of collisions will increase, which then increases the pressure of the system. What we want to do is try to say this whole sentence. We don't want to just quickly jump from more temperature is more pressure. We want to explain why that happens.